Welcome back, everybody. Topic this week is a short repetition of this kind of particle Hall formalism, which we went through last time. And then we are going to repeat some of the machinery behind full configuration interaction theory. And I'm going to use selected example to illustrate what it actually means. And then we are going to also look at the diagrammatic representation in the particle Hall formalism, because that is widely used when you do many-body physics. Thereafter, we will continue on Friday a little bit more with FCI theory. We're going to link this to the Lipkin model, which will form the basis for the first midterm. And then we will, if we get time, and I didn't write it here, if we get time, we may actually start with the Hartree-Fock theory, which is our first mean field theory. And let's see if we have, we have more people. No. Maybe you could. Yeah, we can just leave it open. Yeah, let's do that. This will be on the recording, by the way. It's always fun. Yeah. Okay, so I'm going to switch back to the whiteboard, essentially. You have some of the material here, but then I will basically just use the whiteboard. So let's do that. And let's repeat some of the things which we discussed last week. So where we were was that we defined the expansion of a state, so the exact state. We are making the assumption, so this is FCI. So we are making the assumption that there is an exact wave function, and we just put a label I, a subscript here. And then this gives us the exact eigenvalue, and then we have psi of I. So we are making an assumption that there is such a wave function, and this wave function can then be expanded in terms of a computational basis, where we have assumed that that computational basis is an orthogonal basis. So this is something we can now expand. If this is a many-body state for fermions, then we can expand this in terms of a basis which goes up to a d number of states. So this is the final dimension. And then we have the overlap coefficients between this state and the computational basis state, which is an orthogonal basis. Actually, the exercises we have this week deal with showing these orthogonality relations if you start with a single particle basis, which is orthogonal. So we have assumed then that this basis, phi I or phi j, is now an orthogonal and normalized basis. And this is a many-body basis. In our case, is normally a set of Slater determinants, which then span the whole space of possibilities. I'm coming back to that in forms of explicit examples for a selected type of problems. Now, one of the things which we did last week was actually to rewrite this expression here when we then looked at the ground state. If we select that one, then this will be something which we rewrote as a C0, which is the overlap between the computational basis state for the ground state, or the ansatz, which we have made, which actually is the same as our new reference state or the new vacuum state. And then there is an operator which we call C hat, which we call the correlation operator. And this acts on this reference state which we have chosen, which typically is a Slater determinant for fermions, which is represented by all the single particle states up to the Fermi level being filled. So this operator C is something which we call the correlation operator, because that tells us about the importance of the other states in the computational basis and how important they are as a mixtures into the exact solution of Schrödinger's equation. So we are assuming now that there is an exact state, which is an eigenstate of H, and that this can now be expanded in terms of this orthogonal basis, which we have chosen. And the orthogonal basis is our computational basis. And normally, just to remind you a little bit about what we did in the very beginning, this computational basis is normally defined in terms of a single particle basis, which is orthonormal. So these are the kind of basic, kitchen items which are used in many-body physics. Now, the thing which we did last time was actually to rewrite this operator C in terms of particle-hole excitations. The other thing which we did was to use something which is called intermediate normalization. So we assume that this overlap here, if you multiply with phi 0 and psi 0 and take that overlap, we assume that that one was equal to 1. That means that the weight from the other normalization factors gets shuffled into strength from the other ones. This is just to simplify notation. You don't need to do that, but it simplifies things. So this is normally called intermediate normalization. Now, what we did was actually to rewrite this operator C0 plus C hat in terms of a sum of pH. This is a particle-hole excitations. There is a coefficient, and these are the unknown quantities. And then we have an operator AH of P. So pH here, that runs over all the possible combinations we have: 0 particle, 1, 0 hole, 1 particle, 1 hole, 2 particle, 2 hole, etc., up to n particle, n hole excitations. So this operator, when we wrote it out, if we now skip the term which is C0, which is just a constant, and we look at the other terms, if we look at this specific operator C hat, the so-called correlation operator in terms of particle-hole excitations, this is something which we could then rewrite in terms of 1 particle, 1 hole. So that had a CIA, and then we have an AI dagger, and this continues all the way till n particle, n hole excitations. So that will be given by AB, CD, and then I have a CIJ, AB, and then we have the creation operators for a 2 particle state and the annihilation operators for a 2 hole state. And this goes all the way up to something which I would just write as n particle, n hole. So the number of excitations we can make, if we have, let's say, 4 particles, we can rewrite that in terms of up to 4 particle, 4 hole excitations. So this kind of expansion, which you see here, this is not limited to the ground state. So this is an expansion which you can make for all the states which now are eigenstates of the full Hamiltonian. So just keep that in mind. This kind of expansion is not limited to the state psi 0. However, in the lectures here, we will mainly focus on the ground state, and we will pay less attention to excited states. We are mainly interested in bulk properties as of now. But when you diagonalize, as you will see, you will actually get all the possible states which the system can have, which are defined then by the dimensionality of this matrix, which we discussed last time. So if we now look at the ground state of the system, what we could do now is just to take a specific example, and we are coming back to the full Hamiltonian later. So this is called a pairing model. And now we are just going to write down the possible Slater determinants without setting up the Hamiltonian. So this will be the topic for the second midterm. So this Hamiltonian here is a Hamiltonian which was used by Bardeen, Cooper, and Schiffer when they studied superfluidity and superconductivity. And they actually got the Nobel Prize for introducing this pairing Hamiltonian. And we will look at that one as a second midterm. But now we are going to look at a system which has n equal 8 single particle states, and it has n equal 4 particles. And what we are going to assume now, and you can actually show that this Hamiltonian conserves specific symmetries. So one of the symmetries which it conserves is the total spin of the system, but it conserves also the number of pairs. That means that your Hamiltonian matrix will split in sub-blocks where you have states with no broken pairs, states with 1 broken pair, 2 broken pairs, etc. And the Hamiltonian actually commutes with the number of pairs, the operators which counts the number of pairs. So the number of pairs is a quantity which is conserved. That means that we are going to limit ourselves to a case with no broken pairs. And the ansatz, when we now make a drawing here, we are going to have 4 doubly degenerate states. So this will be a spin-up state. And with 4 particles, the ansatz for the ground state is now that the Fermi level is given by the 2 first states here, P1. And these P's are just quantum numbers of our choice. These are quantum numbers meant to label doubly degenerate single particle states. But when you're making the slots here, you would have 1, 2, 3, 4, and then you have a slot here for spin up and spin down, 7 and 8. So we have 8 single particle states, but we have 4 doubly degenerate states. Here, the states are paired. So that means that when we say a pair, it means that the states are now filling a single particle levels with spin up and spin down. That is a pair. And what Bardeen and Cooper and Schrieffer actually postulated is that the basic Hamiltonian to describe superconductivity had features like this. So you could look at breaking a pair and not breaking a pair, and then construct a Hamiltonian which was then able to give a kind of phenomenological understanding of superconductivity and superfluidity. So this is something which we would label as phi 0. So this is our ansatz for the ground state. And that's the Slater determinant for these guys here. So this will be a 4 times 4 determinant, defined by these single particle states 1, 2, 3, and 4. Okay? So being doubly degenerate means that they have the same single particle energy. And it allows the occupation, every single particle state with double degeneracies allows you to occupy it with 2 fermions. Now, when you now assume that there are no broken pairs, when you do the combinatorics here with no broken pairs, it means that you would need to do the combinatorics of 4 levels. They're doubly degenerate, and you have 2 pairs, right? And the way you can shuffle these around when you do the calculated binomial factor is 6. So actually 6 possible Slater determinants with no broken pairs. When you run the calculation here, this is 4 factorial divided by 2 factorial, 2 factorial, and that gives you just 6. So you can actually illustrate the number of determinants which you have by simply now setting up the other possibilities. So the state which I will label as a phi 1 is now a state which looks like this. So we keep these 2 guys here, but then we promote those in the second doubly degenerate state to the third one. So that means that we have a 2 particle, 2 hole excitation. And since we don't allow for breaking of pairs, that means that there are no 1 particle, 1 hole excitations, because we simply don't allow it. And the Hamiltonian commutes with a pair operator. So you can rewrite the Hamiltonian in terms of pair creation and pair annihilation operators, as you will see in the second midterm. And the specific thing with this nice model here is that you then are going to deal with some simple types of excitations. And when you then do simply the reshuffling of states, you can have this state here, and then you can promote these 2 guys up here. So that's also a 2 particle, 2 hole excitation. And then we can continue by doing this combinatorics. So we can have this one, but now we can promote the 2 in the lowest state up here. So that will be phi 3. That is also a 2 particle, 2 hole state. And then we have the next possibility, which is going to be this one. And then we promote the 2 in the lowest lying state up here. And we would call this for phi 4. And that's also 2 particle, 2 hole excitation, because we are taking 2 states below the Fermi level. So this is going to be, our Fermi level is going to be marked here. So this is our F. And this is again our state F here. No, that was a little bit, I confused myself a little bit here. This is the Fermi level. Okay, let me redraw it here. And then we have the final one, which is pretty easy to see, and that will be a 4-particle 4-hole excitation. So the final state which we end up with is something which looks like this. So we have the Fermi level here, again, F, and then we have this one filled and this one filled. And that is a 4-particle 4-hole excitation. And we just label this as a phi of phi. So when we now are calculating the ground state of the system, we are going to calculate the ground state of the system in terms of a phi 0. And that will be a linear combination of all these Slater determinants. So there will be as factor, an overlap factor, phi 0 plus C1 of phi 1. And this goes all the way up to C5 multiplied with phi 5. And the second exercise we had in the first exercise set was a simpler case where we just looked at 2 fermions. And that already gave you some kind of hint of what is going to come. And these coefficients, ideally what we would like to have is that most of the ground state is defined by this state here, the ansatz we've made for the ground state. But depending on the strength of the interaction, these parameters here can become prominent. So you can mix in excitations. And that depends all on the type of correlations you create due to the forces which act on the system. So some interactions are very weak, like the Coulomb interaction, and then often an ansatz where you keep some few Slater determinants works well. If you have systems which are strongly correlated, then clearly you would need all the components in that basis set, which you have defined as your computational basis. So if we now look at this specific system and we want to rewrite it in terms of these particle hole excitations, what we would have then, and we use intermediate normalization, then this would be written something like a phi 0. So I'm putting C0 equal to 1. And then I would have a 2-particle 2-hole excitation, A, B, I, J. And then I have these unknown coefficients, A, B, and then I have my phi, I, J, A, B, plus, in this specific case, we have only 4-particle 4-hole excitations as the most we can get. So we would have a I, J, K, L, and then we have an unknown coefficient, C, I, J, K, L, A, B, C, D, and then we have a 4-particle 4-hole excitation, which is our state phi 5. So we have an I, J, K, L, A, B, C, D. And this state which you have here is nothing but this single state phi 5, which we defined earlier. And then you can put the indices and so on, but this is a kind of general structure which we're looking after. So what I'm going to do now is just to repeat a little bit of how we move from this one to an eigenvalue problem. And FCI is just you solving an eigenvalue problem with a predefined computational basis. That's the essence of FCI. So if we then look at what we did last time, the basic assumptions we have now is that we have H acting on phi, and I'm just putting an index I here, and then there is an eigens value of psi of I. We will focus at the end, we are going to focus on the ground state only. And the assumption again is that the basis which we are expanding in, this phi ij, phi I, is an orthogonal basis. So when we then set up the energy, and what we can do now is when we rewrite the equations, so let's now focus on the ground state in this specific case. So we let this one go to phi 0. And then we take this equation and we multiply both sides with phi 0. And then we just subtract the right-hand side from the left-hand side. So what we end up with then is something which we want to become 0. So we can rewrite it. So we would have a sum then. And what I'm going to do now is to just rewrite it the way we did last week, PH prime. And then we would have a sum of CHP. And this is the complex conjugate. And then we have CH prime of P prime. So these are the different 0 particle, 0 hole, 2 particle, 2 hole, 4 particle, 4 hole cases, or in general, just a given particle hole excitation. And then what we have next is then the multiplication of the state phi of H of P, and then I have H minus E, 0. So I'm going to let EI go over to E0. And then I have my phi of H prime of P prime, and we want this to be 0. So what I did then, if you now look at this overlap psi of H0, of H, I multiplied with the psi 0 from the left. We know that this is just given by when we write it out in terms of the particle hole excitations, which is just another way of regrouping the Slater determinants. So just keep in mind that what we have done is to regroup the determinants. Then this is nothing but this term here. And then I simply subtracted the right-hand side, and then we require that this equation here has to be 0. So this term here is nothing but what we had here. So what is common then is then to define a function you want to optimize. And we want to optimize this with respect to these unknown parameters C. And this is what is normally a standard path which leads to the eigenvalue problem. So you could define a Lagrangian, which is then given by psi 0 of H minus E, 0 times psi 0. And the psi zeros depends on these coefficients. And then you want to optimize it. So it's a Lagrangian, it's an optimization problem with a constraint. And the constraint which you have is that this has to be normalized to 1. That's a typical constraint you would put on the solution here. And then what we did last week was simply to take the derivative, and it's sufficient and necessary to actually just take it with respect to one of these. So we take it with respect to the complex conjugate, and we want this one to be 0. So we're going to optimize this function. And when we did that, what we ended up with last time was simply a sum, because then we pick P and H. So we have only a double sum over P prime and H prime. And this contains then a phi of H of P, and then I have H, and then I have my phi of H prime of P prime, multiplied with this C H prime, P prime. So keep in mind that this C, this unknown coefficient then contains the information of all the types of particle hole excitations we can have. And this is given by E0 of CH prime of P prime. And then I have the overlap of phi H P of phi H prime of P prime. And we have defined this computational basis to be orthogonal. And this is a quantity which we want to drive to 0. And one of the things we did last time was simply to rewrite this PH, and we defined that with an index J. So that is one particle hole excitation, one of the many possibilities. And then we let this P of H be defined just by a common label I. And then we could rewrite that equation in terms of a sum over particle hole excitations with a label J, which then just points to the different particle hole excitations you can tabulate. And then you have now a state phi of I, and then you have H and phi of J, and this is minus E times Cj. And then, since these states are assumed to be orthogonal and normalized, we have just a Kronecker delta. And this is something you can isolate, and you have a sum over Hij, where Hij is now simply this element here. And we typically call that a matrix element, because when you look at what you have here, this is just the mathematical definition of a matrix times a vector. So when you take a matrix and a vector and you multiply them and you're looking at a specific row in that matrix times the vector, so you take one row in the matrix and multiply with a vector, then what you have is this E0 multiplied with C of I. So you're looking at row I, and that means that you will have a number of rows which correspond to the number of particle hole configurations you have. So if we look at the specific example, we will actually only have 6 rows because we have phi 0, phi 1, phi 2, phi 3, phi 4, and phi 5 in the pairing example which we looked at. So this is something you would also write in a more general way. So you would have a matrix times an eigenvector, and this gives us an eigenvalue E, where we don't need to specify this to be the ground state. And then we have the eigenvector here. So this is a standard eigenvalue problem. So when you now don't specify only one of the one's components, but you look at all of them. So if you look at this vector C, for the example, for the pairing example, then this vector C is just given by these coefficients, which we define to be C0, C1, C2, and all the way down to C5 here. And the matrix H, which we have, would then be given by these matrix elements H00, H01, up to H05. And then I have H10, the matrix is Hermitian, which means that H01 is the same as H10. And this goes down all the way to H50, and it continues to H55 here. So if we now use this Condon-Shortley rules, this matrix element H05, for instance, is just the overlap or the transition probability in this computational basis between a state, which is a 0 particle 0 hole, and a 4 particle 4 hole. So if now the matrix H is, or the operator H is an operator which contains at most a two-body interaction, what should the value be here if you use the Condon-Slater rules? Should be 0. Should be 0, because now we have 4 particle states and 4 hole states. So there's nothing in common between the ground state and that 4 particle hole excitation. And you can view this diagrammatically if you just think of the overlap in the following way. So you have these, the state phi 0, which contains these guys. And then you look at the excited state, which contains these. And you see now that there is nothing in common here. So that's another way of just visualizing graphically the difference between the Slater determinants. So when you're then setting up the, so this is the state phi 5, which is a 4 particle 4 hole state, and this is our phi 0. So you could illustrate it graphical like that, and then you would see immediately that when you take the overlap here, this has to be 0. Then you can actually proceed, and if you look at the Hamiltonian matrix, the way we have defined the states, so you could now think of writing this as a phi 0, a phi 1, and all the way up to phi 5. And then you have a phi 0. So this is essentially the matrix which we are setting up, normally called the Hamiltonian matrix. And we know that the overlap between the ground state and the particle hole excitation, 2 particle 2 hole excitations, does not need to be 0, because we have only 2 single particle states which differ. But then here we would have 0. So this is again this block which becomes 0. And then we would have something which is non-zero here, non-zero, and then 0 here. Now, the way I define these states means that the overlap between phi 1 and phi 4 is also 0. So if you look at this specific number, you can again just make this drawing. So you have 2 here, and then you have 2 here. And then if you take the state phi 4, this is something which we defined as this. So this will be phi 4. And this is our state phi 1. And you see again that if I have a two-body interaction, there is nothing in common here. So because I have two particle states which are different from the states which you have in the other one. So this will again give and the two whole states which are different. So this will again give us an overlap between these two states when I use the Hamiltonian, which will be 0. So the order I have defined means that I will have zeros along the diagonal here. And you're actually going to calculate this. Let me see now. This got a little bit strange. Let me see. 1, 2, 3, 4, 5. There should be 6 here, right? So you will actually get 1, 2, 0. So that should be a 0 here. Oops. And then XX. And that should be a 0. So the matrix which you get then is pretty simple to set up and pretty simple to diagonalize. And this is going to be part of the exercises you will have in that specific midterm, which will be the second one. So if we now look at the E0 case, so we're going to focus on that one. So what we have then is a sum over J, and then we have a phi I of H of phi J of Cj minus, and then we have this to be equal to E0, and this has a Cj, and then I have my delta Ij here. So suppose now that I look at the first row here, because this is a matrix, and this i's here, or when I have the Kronecker delta, I'm going to get an I, and I have 6 rows in the matrix. So let's look at the first row of that matrix. That means that I is equal to 0. So we are looking at phi 0 here. So what we will have then will be something which runs like this. It will be phi 0 times H times phi 0, obviously, and multiplied with C0. And we have minus E0 times C0. So that fits there. But then I have plus, and in this, for the other cases, E0 is going to disappear because I'm going to take the overlap. So when I take phi 0, H, and I have a minus E0 here, that disappears because that's just a constant. And then I have states which are different. So I'm going to get a phi 1 times C1. And then I get plus. So for all the other ones, the E0 term disappears because the basis is orthogonal. So I get a phi 0, and then H of phi 2 here, and then I have a C2, and this continues all the way up to phi 0 of H of phi 5 multiplied with C5. So that would be the first row. When I now go back here and I look at my expressions which I put up here, my H times C equal to E times C. So I'm just looking at the first row in the matrix times the vector. Does that sound okay? Let me know if it's too simple. I just wanted to step through these things. And then if you take the second row, and then you will see the pattern immediately. In the second row, we're actually multiplying with phi 1. As you will see from here, so the second row is actually this guy here, now being multiplied with a vector C. So that means that we have then phi 1 multiplied with H minus E0, which we picked, and then we have phi 0, and this contains C0. The next one is phi 1 of H minus this E0 of phi 1 multiplied with C1 plus, and you see now for the first term, E0 disappears. For the second term, I do actually have the E0 multiplied with C1. And then you see that you have a phi 1 of H minus E0. And in this case also, E0 disappears because we have a constant and then an overlap between two orthogonal states. And this goes all the way up to the final term, which is phi 1 with H minus E0 times phi 5. Let me just wipe this out and rewrite it on the next page. So the final term here is then plus, and then I have phi 1 of H minus E0, and E0 disappears, multiplied with C5. And then you see that this is actually nothing but us writing out the matrix H times the vector C. And this is equal to E0, which we now have picked as the ground state, multiplied with C. If you write it out row by row here. So when we now sort this, we are going to get a set of equations. And you can see that quickly that the first row gives us J equals 0 up to 5, the number of states. And then we have phi 0. And then I have H multiplied with phi of I times these unknown coefficients. And this is E times C, E0 times C0. The second row gives us J equals 0 up to 5. And then I have phi 1 multiplied with H. And then I have phi of I. And then these overlaps. And that gives us again E0 times C1. And then you can continue to the last one, which is just J equals 0, 5. And then I have a phi of 5 here of H times phi of I. And in this specific case, in every one of these rows here, what we have to be a little bit careful with is that we have isolated the case with C0 in the first row, with C1 in the next one. So in this particular case, we have that J, for this one, we need to put a constraint that the J is different from 0, because I have isolated 0 on the other side. In the next case here, J is different from 1, because I've isolated the 1 component on the other side. So you have to be a little bit careful, because the case with E0 is a case which actually this notation is a little bit clumsy, because I'm summing over all of them, but it's only the case with J different from 0 which gives us the J equals 0, which gives us something which has E0 with it. And then the final one gives us now E0 times C5. And in this specific case here, we also have, when we rewrote everything in terms of this guy here, this one, then we have isolated the E0 case. So when I wrote this notation, it means that the E0 case is the one which pops up here, and the same here, and the same here. But we have to run over all the J values for the expectation or these transition matrix elements of the Hamiltonian with a given Slater determinant. But it's only the E0 term, which is just a constant, which brings something which is different from 0 on the right-hand side. So the way you would actually solve this problem here is simply to set up these matrices, and then you would diagonalize. And when you diagonalize, you obtain these coefficients Ci, C5, C0, etc., etc. So the full configuration interaction theory means that you need to set up these matrix elements here. And there you can go back to the Condon-Slater rules and find the analytical expression for these different terms. So what I want, this was a specific example. So what I wanted to do now is to go over to the general case so that you can see what these expressions will look like, because that will also allow us to define something which we last time introduced as the correlation energy. So let's go to the general case in terms of a particle-hole excitation with particle-hole excitations. And we have up to n particle, n hole excitations. So now if we look at the first row, we are going to rewrite that in terms of particle hole excitations. So the first row is the one which involves phi 0. So what we are going to get then is, assuming now that we use this intermediate normalization with C0 equal to 1. So I'm going to get the following when I write it out. I'm going to have H minus E0 times phi 0. Then all the other terms are going to be given by the following. So I will have a sum over AI. There is a one particle, one hole excitation. And I'm going to have my phi 0 multiplied with the Hamiltonian. But then the E0 term drops out because the one particle, one hole state is orthogonal to the zero particle, zero hole state. So I'm going to get the minus E0 term, which will drop out. So I'm going to have a phi of IA like that. But the E0 term drops out as we had before when we looked at the first row. And then we get a new contribution. And then we have an A, B, I, J. We have this unknown coefficient, which we get when we diagonalize. And then we have a phi 0 of E minus E0. And this E0 term will drop out again because we are actually missing, or rather we have the states which will be orthogonal. And this continues all the way till the final n particle, n hole excitation. And I'm just going to write this as an n particle, n hole. And I have my overlap with phi 0 of H minus E0. And then I have the n hole and n particle ansatz for the wave function. And then I have a coefficient which couples these two guys. Now, if I have at most a two-body interaction, then the only terms which survive with only a two-body interaction are actually these first terms here. All the other terms, because we are linking a zero particle hole state with a three particle free hole, four particle four hole, etc., they are automatically equal to zero because we have states then which will differ with more than two single particle states. And then we can use the Condon-Slater rules and simply state that for this specific interaction we have, which is a two particle interaction, we end up only, and this is where it's appropriate to take a break, with at most a two-body operator. At most a two-body operator. What we will get then is phi 0 with the overlap, or no, not the overlap, but the expectation value of phi 0 minus E0, which is a true eigenvalue, plus a term which runs like AI, CIA, and then I have the matrix element, which we are going to place in here after the break because we calculated that one last week. So we know what that looks like. And we have a final term, since we're only dealing with two-body interactions. And then we have AB, and then phi 0 of H, and then I have my phi I, J, and AB. And after the break, we're going to plug in the values for these ones, or the expressions for them, not the values, but the expressions, because we calculated these expressions last week. And then we will have a compact expression. So if somebody gives you these coefficients from diagonalization, you know how to calculate the energy. Clearly, this is a little bit stupid because when you diagonalize, you have that energy. But so what I'm going to do after the break is actually to use this kind of expressions for the first, the second, the third, etc. rows in order to solve the diagonalization problem in a very stupid and inefficient way. But the reason why I do that is that that will link to all the other many-body methods which we are dealing with. Because all of many-body theory, the way we have expressed it now, deals with finding either the exact coefficients or an approximation to the coefficients. And when we do perturbation theory, you will see that we will get an analytical expression for these according to the order in perturbation theory. When we do copper cluster theory, there are explicit expressions for these which we can obtain. So all the many-body theories, when you cannot diagonalize the problem because it's too large to diagonalize, then you will find approximations to these coefficients here. So after the break, I'm going to solve these equations in terms of non-linear uncoupled equations, which will have to be solved iteratively. And that's a stupid way when you cannot diagonalize, but it allows us to link with the other methods. And then hopefully you can see the mathematics between FCI and the other many-body methods. So FCI is a kind of ideal if you can diagonalize. But normally the dimensionality of the matrices are so large that you cannot do that. And then you have to resort to approximations. And that's what many-body theories are about. So the thing I wanted to do now is to actually plug in the explicit expressions. And then I'm going to show you this type of inefficient way of solving the equations. But I'm going to use that one to point to what kind of approximations different many-body methods actually imply. So when you look at this expression here, one of the things which we defined or calculated last week, which is more correct, if we look at this specific overlap, this is something which we found to be equal to the state I, and then I have this F and A. This is the matrix element or the integral, which we would then plug in. And this was given by the integral, where we have the unperturbed or non-interacting part of the Hamiltonian, which then could be kinetic energy and the eventual external potential. And then we had a sum over all the states below the Fermi level, and we had this anti-symmetrized matrix element of A and J, anti-symmetrized. So this would be one specific contribution, which we can just plug in directly. And then we also had, or we calculated last time, this transition which we have here between a two-particle, two-hole state and the zero-particle, zero-hole state. So let's just quickly remind ourselves about that term as well. So we have a phi zero over V, actually H. This is the total Hamiltonian. And what we found then is that this term here is the same as AB, V, IJ, where this V is again defined by this anti-symmetrized matrix element. The thing which we calculated last time was actually this one, AB of phi zero, and that gave us just IJ of V, AB. And by hermeticity, these are supposed to be the same matrix elements. So we can then collect things, but what we're going to do as well is to redefine this term which you see here, or these two terms. So this is the exact energy for the ground state. And this one is the one which we calculated as a reference energy. So to quickly remind you, this expectation value between the vacuum state and the Hamiltonian here is something which defined the reference energy. And in our case, that was given by the sum over all the states below the Fermi level of J, and then we have these integrals with the unperturbed part of the Hamiltonian, plus a 1/2, and then we had a sum IJ still running up to the Fermi level only, and then we have V and IJ anti-symmetrized. So it's common then to define a quantity which is called the correlation energy. So if I shuffle these two terms here over to the right-hand side, because what you have here is that this expression here has to be equal to 0. So I'm going to shuffle these two terms over to the right-hand side, and then I'm going to define something which is called the correlation energy, which is the difference between the reference energy. So the reference energy serves as a kind of starting point for your calculations. And then the difference between the reference energy and the exact energy brings in the information of all the types of correlations which you have beyond this phi 0. So this part which you see here brings also a type of correlations into the picture, because what you're looking at is the effect of the Pauli principle to first order, because you have a direct term and then you have an exchange term. So the Pauli principle kicks in here, and that brings a kind of correlations in. But then all the other terms which you see, they bring correlations beyond those which you would get by calculating the expectation value of the Hamiltonian with a vacuum reference state. And hopefully these terms may be small. If they are large, that typically means that the reference energy you've chosen may not be the best reference state. So we define then the reference energy as a delta, or the correlation energy as a delta E. So this is a quantity which we will call the correlation energy. And often in many body physics, you will see that people present the correlation energy instead of the total energy of the system, because then you can study the differences which different many-body methods may give you. So this is now going to be given as the energy of the ground state. This is the exact energy minus this reference energy which we can calculate. And this is going to be equal, in this specific case, when we sum over particle Hall states with a two-body interaction only, then there are only two terms, and one of them is now given by I of this term F of A plus this next term, which is A, B, C, and Ij. And then I have a Cij, AB, and then I have these integrals, AB, and then anti-symmetrized. So that's a pretty compact expression we have for the first row in these expressions. And then the thing now is that obviously we don't know these coefficients unless we diagonalize. So when we diagonalize, we would get these coefficients. So they would come from diagonalization. But if we don't have them, we could then have some guesses, or we could use different many-body theories to actually find them. So if we now move on a little bit and look at the second row, and we perform the same type of exercise as we did before. And as I promised you, this is a very inefficient way of looking at things. So the second row will contain the following, because we are multiplying with this a given state. So multiply with one possible particle Hall excitation, with one possible. And remember now that there can be many. In principle, you have an infinite basis, so you can have an infinity of one particle, one Hall excitations. But now we're picking with one possible, one particle, one Hall excitation. And I'm simply going to label this as a phi of I with a particle state A. And then I'm going to perform the same multiplications. So I will get a term now with the first contribution, which comes from the ground state ansatz. So this is going to contain an H minus E0 multiplied with phi 0. And in this specific case, the term with E0 disappears because these two states are by definition orthogonal to each other. And then I have the next term, which now contains all the possible particle Hall excitations I can have, one particle, one Hall ones. So there's going to be a coefficient CJB, and then I'm going to have a phi of AI of H minus E0 multiplied with phi of JB. So that's the next term. And then this gets a little bit more complicated, and you will see that it's not a very efficient way of solving the problem, because if you can diagonalize, you wouldn't solve the problem as a set of nonlinear coupled differential equations. And you will see the nonlinearity is actually coming from the term which you see here, the E0 term. So if you look now, you have a term CJB. If you look at the E0 term, if we go back, you see now that this E0 here contains this term here and also this term. So what you're going to get now is a set of couple equations in the unknown parameters C, but they will be nonlinear because this term here is first order, so this is linear, but then we have a new term coming in here. So then we have a second order term in terms of this C I A, the one particle, one hole terms, and also the two particle, two hole, etc., etc. So you can always rewrite a diagonalization problem in terms of coupled nonlinear equations in the coefficients, in the unknown coefficients C. This is just a way to rewrite a diagonalization problem. But the reason why I'm doing this is that it's going to link us, give us a link with other many-body methods. So please just be a little bit patient because the algebra here is not the most exciting one. But hopefully then you will see the benefit of it. So this contains now a specific state, which we have singled out, this IA, this one particle, one hole excitation. I have an E minus E0, but now the E0 term will disappear again because I have a two particle, two hole excitation, and that term is just a constant. So we'll have a BC, so this is my two particle, two hole guy. And since I have a one particle, one hole state, with a two body interaction, I can connect with a three particle, three hole interaction, no state. So there has to be a new one here, which now runs over B, C, D, and J, K, L. And I have an unknown coefficient, C, J, K, L, B, C, D. And then I have my phi I, A, H minus E0. And again, E0 disappears. So this should be a minus sign. And then I have my phi of J, K, L, of B, C, D. And it stops here because four particle, four hole states cannot link with a one particle, one hole state due to the fact that we have only a two body operator at most. So that disappears, or that gives a vanishing contribution due to the Condon-Slater rule. So if we look at this term here, we can simplify this because we see immediately that this term has to be zero. Also, since this is a constant, unless J and B are equal to A and I, the E0 term will disappear. So that means that when we rewrite it, we are going to get the following expression. Now I need to just look again what I had here. So we are going to get a phi I, A, and then I'm going to have H with phi 0. That's the ground state overlap. And we have already calculated that matrix element. We found it last time. And then we have a plus, a state, or it's actually a minus here. When we go back to this expression, there's going to be a contribution here where we have J and B equal to I and A, and that will give us a non-zero contribution when we have E0, and that's the only one which is non-zero. And then I have a minus E0 times CIA, and then I have the next term, which runs like a sum over J and B. I have the unknown coefficients, and then I have the integrals, which involve these specific states. And then in addition, I get the two body piece. I get B, C, J, K, C, J, K, B, C. And then I have my phi of IA of H. The E0 term disappears. So I have a J, K, and B, C. And the final term involves a free particle free hole excitation, which now implies a sum over all these guys here. C, J, K of L, of B, C, D. And then I have my phi of A, H, of phi of J, K, L, of B, C, D. Now, when you look at this, in order to start the solution of this type of equations, and you're going to get a similar one for the two-particle, two-hole state when you multiply that one and get the third row. So then you will get the equations for the two-particle, two-hole, the three-particle, three-hole. So if you look at your matrix, which you're setting up now, you would get for each row in the problem here, if you look at this one, you will get one row from this term. That was the one which defined the correlation energy. You get one row for the one-particle, one-hole excitations. You get a similar one for the two-particle, two-hole, etc., etc. In this specific case, in the model which we picked, we actually had only two-particle, two-hole excitations and four-particle, four-hole ones. And we had 4 two-particle, two-hole states, which means that if we were to translate this one into the problem here, we would have a limited number of one-particle, one-hole states, for instance. If you look at these equations here, in order to be able to solve this numerically, you need to have a guess. And that's the only way you can actually start the solution here. So when you solve equations, nonlinear equations, they are normally solved in an iterative way. So which means that you would set a guess for these terms here. And you have to make approximations then, because you will get a more complicated equation for two-particle, two-holes, which will be the third row. You get even more complicated ones for the three-particle, three-hole, etc., etc. So at some stage, you have to make some guesses. Now, the typical guess you would do then, when you start the equations, is that you leave out this one in the first iteration, and you leave out that one, and you also leave out this one. And then you can find an approximation for this one. So let's try that. And you're going to do the same thing with the two-particle, two-hole thing. So let's take a look at it. So in order to solve iteratively, to solve nonlinear equations in the unknown coefficients, equations in the unknown coefficient C, known coefficients C, we need to start with a guess for the first iteration. We would solve this iteratively. We would solve the equations, we would solve the couple equations, iteratively. So that means that for CI, A, we would have a guess for the first iteration or the 0th iteration. And what we will do then is simply to say that we get the following expression. So if we look at the expression which we had, we are going to put everything which is beyond the first line, we're going to put that to 0. So that means that, and we know this expression here. We know what that one looks like. So that expression says that I have an A, and I know how to calculate this one, times I is equal to E0 multiplied with this CIA. And this is going to be the value which I'm going to make a guess for. Now, the problem which we have is that E0 depends on this CIA. So if you look at E0, we found that one to be equal to the reference energy, which we can calculate, which is known. But then we had this term, which actually depends on CIA. And then we have now a term here which contains the specific matrix elements, this I of F of A plus the term of a Cij, AB, and then I have my Ij, V, and AB anti-symmetrized. So what you see now is that even this term, E0, contains the unknown coefficients. So what is common then is simply to pick the result from the reference energy. So we would then take the reference energy, and from the reference energy, we would just take the single particle energies, which are known. So we would then pick this one, so we leave this one out, because we don't know it. And then we simply replace this E0 with the reference energies. So this E0 then is then approximated with the E0 from the reference energy, which is further approximated with just the sum over the states below the Fermi level. So that's a pretty simple approximation which can be made. So then we have a starting value for these coefficients. And remember that these coefficients have to be dimensionless. So that's why we have this term here, obviously represents energy. And then this term here represents energy. Energy divided by energy is a dimensionless quantity. So this is the way we would proceed, and then you have a guess. That guess may be a good guess, or it may be a bad guess. We don't know that. The thing now is that when you do this, when you set up this expression here with just the single particle energies, which you have here, so these epsilon j's, then as we will see later, that means that these coefficients are going to be given by what we will get in perturbation theory. So if you do many-body perturbation theory to second order, you're going to get coefficients which look like this matrix element, or this integral, divided by these unperturbed energies. And that's something which we are coming back to. And you will see the explicit expressions for that. Then you can do the same thing with the coefficients Cij, AB for two particle, two hole. You can skip essentially all the terms because you're able to isolate something like this. And then you would skip all the other terms and then find an expression which is given by a two-body matrix element divided by the unperturbed energies. And that will give us coefficients Cia and Cij, AB, which are the same as you would get analytically in perturbation theory to second order. So this is something we will come back to. Methods like copper cluster theory, they actually try to sum these coefficients, specific correlations, to infinite order. But copper cluster theory is actually an approximation to what you see here, but where you leave out these terms. So you can actually make truncations at the level of one particle, one hole excitations and two particle, two hole excitations. And then if you keep all equations with two particle, two hole and one particle, one hole, you're then summing to infinite order all these type of excitations. So remember that when you diagonalize, you actually have a non-linear dependency of these parameters, and you're actually summing the contributions to these guys to infinite order when you diagonalize. So copper cluster theory allows you to calculate efficiently a subset of these type of parameters where you actually leave out specific types of excitations. But then you can solve the problem exactly with those types of excitations. So this very clumsy, inefficient way of solving a diagonalization problem by rewriting it as a set of coupled nonlinear equations is something which we will come back to later when we introduce many-body perturbation theory and copper cluster theory, because then you can see the links here. Now, if we do Hartree-Fock theory, what we are doing then is actually that we leave out all these other excitations, and we are only interested in these CIAs. That is essentially the essence of Hartree-Fock theory, which is going to be our next many-body method. So FCI is in a way the method of choice if you can diagonalize, because then you get all the states, you get the eigenvectors, If you cannot do that, then you would have to think of truncations of your problem. And that means that you have to find ways by which you can reorder the type of approximations you're doing. And Hartree-Fock theory is actually, and this is something which we are going to dive into tomorrow. So Hartree-Fock theory, if we now look at this type of excitations, and I think I put it up here. No, I didn't put. So what Hartree-Fock theory means, I thought I had put it up. So all these many-body theories, when we are implementing them, what they actually mean, or they can be understood as, is a subset of unitary transformations which zero out specific matrix elements. So when you look at the setup which we had just some, I think it was last week, when we look at the Hamiltonian matrix in terms of particle hole excitations. So we have a block with 1 particle, 1 hole, 2 particle, 2 hole, 3 particle, 3 hole, etc., up to n particle, n hole. And then we have the rows which represent the same type of states, 2 particle, 2 hole, and down all the way to n particle, n hole. So what we've seen is that if we use this Condon-Slater rule, there's a specific structure here. And that structure says that we have some non-zero matrix element here, here, and here, if we have a two-body interaction. These guys are all zero. We have non-zero matrix elements here, whereas all these other guys are zero. We have a non-zero element here, and then we have zeros. And then we have zero, non-zero, 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 and that is zero thereafter. I'm just putting it like this. So when you diagonalize a matrix, what it means is that you have an orthogonal transformation of your Hamiltonian. So the diagonal matrix which you get is given by a unitary transformation which acts on your originally Hamiltonian matrix like this. And these matrices are either unitary or orthogonal, depending on whether they're real or not, or Hermitian matrices. And this is equal to ut of u, and this is the identity matrix. So since the matrices are going to be pretty large, it's very unlikely that you will find a unitary transformation which applies to the whole problem. Because if you could do that, then you would diagonalize the problem, and then you solve your many-body theory. The only thing you need to do then is to calculate these different transition matrix elements, as we call them, or just matrix elements, which are integrals. And then you would use the Condon-Slater rules to find all the contributions to the Hamiltonian matrix. So ideally, what it means when you can diagonalize is that it's only the matrix elements along the diagonal which survive. And these are the eigenvalues. However, when you now introduce different many-body methods, what they are going to do is to do some subsets of unitary transformations. So you can think of different many-body methods in terms of linear algebra. So when we do Hartree-Fock theory, what happens then is that we have a linear or a unitary transformation where we zero out the 0 particle hole to 1 particle hole matrix elements. This is the essence of Hartree-Fock, if you think in terms of configuration interaction theory. When you do copper cluster theory, what you can do then is that you can zero out 1 particle, 1 hole parts, 2 particle, 2 hole parts, but the remnants here will always be there, but they will be changed because you're performing a unitary transformation. So since the problem is so big, you will always deal with some subsets of excitations, and you can zero them out, which means that you have a smaller unitary transformation, orthogonal transformation, which zeroes out specific blocks. And then you can hope actually, that the remnants here, the other matrix elements, are very small, and that perhaps allows you to reduce a diagonalization problem. Or you would just stay with a specific many-body method and then simply say that these other types of correlations are negligible, and I'm only interested in these types of correlations here. These would be approximations to the full many-body theory. So the full many-body theory, if you can diagonalize, then you solve the problem. And FCI would be the method of choice. But since we have an infinity of degrees of freedom, this clearly is going to be, reality is going to be far from this ideal here. Okay, I thought of doing one thing now. Instead of introducing new topics, I wanted to let you digest these things. And then tomorrow, we are going to look at a diagrammatic representation. And we will then also start looking at this Lipkin model, which will be relevant for the first midterm. And then if we get time, I will start with Hartree-Fock theory, which is the basis for mean field approximations. And as I said, what Hartree-Fock theory is going to be is actually you finding a unitary transformation which zeroes out this block here and this block here. That unitary transformation acts on all the other matrix elements. And it will change this one, it will change that one, and it will change this one, but it zeroes out a specific block. And your hope then is that the ground state energy you get is closer to the true ground state energy. So I want you to keep this kind of linear algebra way of thinking, because that can build up the kind of intuition about what the different many-body methods are doing. So if you're like me, who loves linear algebra, this is the way I actually like to understand the problems, because then you can immediately link to the different methods a mathematical interpretation, which can perhaps be easier than just us going through this, all the different derivation for specific many-body method. Does that make sense? I'm assuming that you remember all these things about linear algebra, right? And what unitary transformations mean. Does that ring a bell, by the way? Yeah, okay. You will see me repeating this. And when we come to this midterm with the Lipkin model, where we have a very small problem, which is easy to diagonalize, then we can actually see the effect of Hartree-Fock theory, which then actually corresponds to us zeroing out a specific block of matrix elements. Okay, I'm going to stop here now. Feel free to ask questions.